Physics Bites,
Physics Bites,
a science podcast in English by the students of Notre Dame.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre Dame de Sion here in Paris. Here we will have two of our senior students, experts on special relativity, who are going to talk to us about this, the revolutionary theory of Einstein from 1905. We're going to try and get into what the basics of it are, what some of the strange and weird consequences of it are, and how it was such a revolutionary theory and how it's still with us today. So, to get started, I'm going to let them introduce themselves.
So my name is Rose.
So we have Rose, and Rose, you've been a student of mine since last year. And then we have...
my name is Rayan.
Right, and Ryan, you've been a student of mine for at least 2 years, since grade 10. And if I'm not mistaken, you're both doing physics majors this year.
Yes.
Yeah.
And hoping to get into the sciences next year.
Mm-hmm.
Yes.
Very good. So this is right up your alley. So without wasting any more time, let's get right into it. What is special relativity?
So special relativity is one of the most important papers that was ever published in the field of physics. It's basically an explanation of how speed affects mass, time, and space. And as it's in its name, it applies to special cases. So it's mostly when we're talking about ultra-fast speed, astronomical distances, without the complications of gravity, since Einstein officially added gravity to his theories later for general relativity. So we talked about first what was physics before, because as you were saying, it was revolutionary, right? Mm-hmm. So before relativistic physics, it was the Newtonian physics.
Right, what we call classical physics or classical mechanics, yes. Anyways. Yeah.
Yeah. So we first talked about the 3 laws of Newton.
Right.
And also how Einstein came up with his theory.
Mm-hmm. So how did he come up with it? Let's get right into it. What is the germ of the idea for special relativity? Why did he feel the need to take Newtonian mechanics and change it?
Because in the classical mechanics, yes, there was something that couldn't be explained, and it was the behavior of light. And so after, obviously there was some scientists before Einstein. There was James Clerk Maxwell's equations, which established that for any electromagnetic waves, especially light waves, there had to be a medium for them to propagate.
Right, at least that's what we thought, because we knew the behavior of waves, and waves were always vibrations in a medium, and so it was natural to say that, okay, well then light, being an electromagnetic wave, should be vibrations in some sort of a medium, which they called...
an ether.
An ether, okay.
Yeah, just like sound, sort of.
Right, which is in the air.
Yeah. And so the ether was an hypothesis, and the Michelson and Morley experiment proved that it actually did not exist, and therefore that the light was traveling at the same speed in any direction.
Right, and regardless of the movement of the instrument that we're using,
in the experiment,
or the Earth. Okay, which is the key point, right? And why was this a problem?
It was a problem because theoretical results said that the ether had to be there. Otherwise, light would be independent when it was traveling in a vacuum.
Right. And this was also in violation of one of the most basic tenets of physics, which is going back to Galileo, the idea of relativity of movement, right? That your movement is based on the frame of reference you're in. Stuff we do in grade 10 already, right?
Yes. That you can apply the law of motions in any referential that's in inertia.
Right. And this was not working with light. So the idea being that, for example, if you're driving a car at half the speed of light and then you turn on the lights, anybody, regardless of their movement, was always going to measure the same speed for light, regardless of the speed of the car, which is not the case. If you're in a car and you throw a ball ahead of you, the speed of the ball, based on whether you're on the side of the road or in the car, would be different, because you have to take into account the speed of your frame of reference.
Yeah, it will add up.
And light was not behaving in this way. So this is the germ of the idea. And so what were some thoughts to explain this before Einstein, and how did Einstein have the solution? Right.
Yeah, Einstein faced this problem because in one hand he has the theoretical results that require the existence of the ether, but in the other hand, with the experiments that proved the inexistence of the ether, it was kind of paradoxical. So that's why Einstein, with his theory, showed that the both opposite idea were possible in the same. They are not opposite actually. So to maintain these two principles which seemed incompatible, he provides an implicit assumption about the space and time. So that was how he came up with his theory.
So just to be clear, when you're talking about these two apparently paradoxical, at least contradictory results, you're talking about, on the one hand, the relativity of movement, which depends on frames of reference, and the other result being the fact that light was not behaving at all according to this. So what was Einstein's solution to reconciling these two things that didn't seem to go together?
So Einstein tried to extend it to all physics, just not the Galileo invariance principle, in order to combine the paradox, sort of, like those two aspects of physics that contradicts themselves. And so he just said that time was relative and was not absolute. And that was, well, said it like that, it's maybe kind of weird, but he imagined a light clock that helped us visualize, at least when we did our presentation, where his idea came from, at least.
So just to be clear, his idea was that, okay, if there's everything is relative, is dependent on the frame of reference, and light is not the one thing that is not like that, then maybe everything should be based on light for measurements of time, space, and eventually mass as well. So that's why he came up with the idea of a light clock, right? Mm-hmm. Okay, go on.
And so with his light clock, he imagined two referentials, because, well, it's not the same anymore, depending on your referential. Mm-hmm. And so he took, for instance, an example. I mean, we took an example.
Yeah.
That
in his name.
Yes. For two observers, one being inertial compared to the clock.
Okay.
And another moving.
Right. So in one case, we have a clock that is not moving in your frame of reference, and in the other one, it is moving.
It is moving, yes.
Okay, with a constant speed.
And so it's kind of hard to imagine a light clock, but it's as if you had two mirrors, and the light traveling from one mirror to another, it takes like 1 second.
Okay.
And so it's like going back and forth like that. Mm-hmm. And so for the observer, that's...
And traveling the distance, which is twice the distance separating the two mirrors.
Oh, yes, yeah. And so for the observer, that's motionless relative to the clock.
Right.
The path has the same distance over and over again, and the duration of a second is the same.
So imagining that, for example, we take this clock and we put it into a car, and the car is moving along. There's one person in the car with the clock, so compared to that person, the clock is always immobile.
Exactly.
And so for him...
But for the person that's outside the car, it will not be the same. Because therefore, the light will take... It would be like a sort of diagonal in order to reach the middle of the mirror.
Because the mirrors are moving with the car.
Exactly.
Compared to him.
And it has to reflect on the mirror. So the path that a light will take will be longer than for the observer that's in the car.
Right.
But it's still a second.
Right. Because we're defining a second as one back and forth for that light beam.
It's just that the second is not the same.
Right.
For the two observers.
Right.
And with that example, we understand that, yes, time is relative to your referential.
Right.
And your speed as well. And that's what Einstein develops in his theory. And we have a ton of consequences that go after his theory and his idea.
Right. And this is what's revolutionary, is that the idea of a duration not being constant, and the duration between the same two events observed by two different people being different depending on their motion, this is what is completely out of left field for the times, right? This is what was completely new, and as you said, there's going to be consequences of this. So let's get into some of the consequences. What are some of the consequences of this phenomena which we call time dilation?
So one of the main consequences is we define that time is not universal, so it's dependent on the reference and the speed of the object. So one of the main consequences is if the simultaneity. Sorry. So this concept is a key idea in this theory. So it challenges the classical notion that time is absolute. And the two events occurring at the same time in one location could also occur at the same time everywhere.
So just so we're clear, what do we mean by simultaneity? What does that mean in the most classical sense?
It means an event, if you consider two clocks in two different cities, they will the time will pass at the same speed. It will the two events of, for example, reaching 3 o'clock. It will be at the same time.
Right. So the idea of two events being simultaneous, that means that they happen at the same time coordinate. And this is something which we take for granted, right? So if I take two objects and they're falling to the ground, I have two glasses and they fall to the ground, we would all agree that they break at the same time. So the breaking of the glasses would be simultaneous. And you're saying that with Einstein's theory, this idea of simultaneity is just as variable as the duration of time, right?
Yeah, exactly.
Okay. How is this posing a problem for us? Why is this so strange?
Because since a long time we define that time as something universal, right. And it's kind of challenges the years of science before Einstein.
Right, and I think some of the other consequences would be, for example, when we talk about causes and effects. Well, a cause always comes before an effect, right? So if we can't agree on two things happening at the same time, which means that for some people A might happen before B, and for other people B might happen before A, in which case it would be problematic for the notion of causality, right?
Oh yeah, and exactly. I think it also generated a lot of questions philosophically.
Yes.
About time and stuff, and it just made people question everything that they had taken for granted before.
Right. So before we go any further, let's talk about some of the other consequences. So you talked about time dilation, you talked about the problems of simultaneity being also relative and not absolute. What are some of the other consequences of this Einsteinian sort of relativistic way of looking at things?
So one of the other consequences is called the length contraction. Mm-hmm. So it's a phenomenon where the length of an object moving relative to an observer decreases along the direction of the motion. So we can calculate this contraction with a formula with the length of when the length of the object measured in a stationary observer equals the length of the proper length of the length in the object frame times this Lorentz factor that we are going to explain. So when the speed of an object approaches the speed of light,
yes,
its length in the direction of motion appears shorter to a stationary observer.
So it means that if I have a ruler that's 30 centimeters, right, when it's immobile in front of me, if it starts moving across from me, I would see it become shorter and shorter in the direction of its movement.
Yeah, exactly.
And the faster it gets to the speed of light, the shorter it will seem.
Yeah. But actually, this doesn't mean that the object is physically compresses, but it's more the length is perceived differently because of the speed of the light.
Okay. There was also one of the consequences also on the mass of an object, apparently.
The mass of an object is not fixed when it moves at a speed close to the speed of the light. So the mass is increased with the relative velocity. So it's also a formula where we have the proper mass times this Lorentz factor equals the relativistic mass. Right. So basically, the faster an object moves, the more it resists to accelerate further. So in other words, this inertia increase. So this explains when object mass is increasing when it's approaching the speed of light.
Right. So, and what happens when we reach the speed of light? For time dilation, for length contraction, for mass dilation, what happens if we actually reach the speed of light?
Well, I think when it reaches, for example, for an object, its mass becomes infinite, and for its length, it's become like a
Zero.
Zero. Yeah,
Yeah.
basically it tends to zero. So because of the mass.
So this Lorentz factor, what is this Lorentz factor? Because you've mentioned it a few times, both of you guys. What is this Lorentz factor?
So the Lorentz factor was established when we did the entire demonstration of the time dilatation formula.
Right.
And this is basically root 1 minus the speed of the object divided by the speed of light, the
Squared.
entire thing, squared.
Okay.
And so it demonstrates like when the object reaches the speed of light, the root will almost be 0.
Yes, because you have 1 minus 1 almost, and then it's
Yeah.
going to be in the denominator. Okay.
Which is why the denominator will just be smaller and smaller, and then the number will be huge.
Right.
Infinite, almost. Yeah.
So the speed of v being almost equal to c is like an asymptote. It can actually never get there, because if it does, it's going to go to infinity.
Yeah.
Which is one of the reasons why we say that we can get close to the speed of light, but not at the speed of light, or crossing the speed of light at least. Okay. So these are the basic ideas behind special relativity. So most of what you guys showed us was all calculation. It was all theoretical, right? Is it just a theory? Is it just a theory that hasn't been tested? Has special relativity been tested? What has been tested? What results did it give?
I think the first application that I'm thinking about is GPS's system.
Okay.
I guess, it's the most striking one, maybe.
Okay.
Because without special relativity, our GPS's system simply wouldn't work.
Okay.
Because the satellites that are orbiting around Earth experience time differently than people on the ground due to both their speed and their positions in Earth's gravitational field.
Right.
So what happens is that I think we're talking about a difference of really microseconds. It's really, really small. But this tiny difference is enough for the satellites to have a shift of like kilometers.
Right,
like
because
10
it's something that
kilometers.
accumulates, and
Yeah,
also
it builds
because
up. Yeah.
even a few microseconds, when we're talking about the speed of light or speeds close to it for transmission, it could be differences of hundreds of meters apart, right? V equals d over t. Okay, okay.
And so
we have to take into
uses
account.
the equations.
So we have to take into account. You said the speed of their movement and also
Their
the
position.
gravitational field.
Exactly.
Okay.
I think also gravity has a part in this because satellites do experience different gravity, but it's not speed. It's not special relativity. Sorry, it's
That's
therefore
general relativity, right? Which is the big brother of special relativity. Special relativity. So, what does the special in special relativity refer to? Do you know? What's so special about it, and why is the other one more general?
It's a special case.
Yeah.
Right. And what is the special case? I mean, why? So to be clear, special relativity is limited to a very specific sort of regime. And do you know what that is?
Yeah, so when you are talking about huge energies, extremely fast speeds, and things that are not applied to our life in general.
True, but I think what the main idea, the reason it's special is because we're talking about only studying movement in what we call inertial frame of reference, what you would call Galilean frames of reference, right? Not accelerated ones. And once we take into account accelerated movement and accelerated frames of reference, that's when gravity starts showing up, right? With what we call the equivalence principle, but that's kind of beyond the scope of what your presentation was about. Okay. I think you mentioned also one of the first tests of special relativity in the 1960s, if I'm not mistaken, with the atomic clocks in the airplanes. Do you remember that?
No, I don't think we mentioned that.
No?
Actually.
Okay, maybe it's a
No.
previous...
I think Rayan did talk about particle accelerators.
Yeah.
Right, that's also... This is a bit more advanced, I suppose, application. But the idea of the clocks was that they literally tested time dilation. They took two atomic clocks, which were synchronized to the nanosecond, and put one of them in an airplane and the other one on Earth. And the airplane flew around for about a few hours. And then it came back down. and they compared the two clocks, and not only were the two clocks not showing the same duration, the discrepancy between the two of them was exactly what would have been predicted by Einstein's special relativity time dilation. So that was one of the first huge confirmations of the theory, the fact that it's correct. So let's get to some questions about why is it that clearly special relativity is a theory that has been tested many, many times, and we take it into account. So it's basically a fact. How is it that we had to wait until 1905 for somebody to come up with this idea? Why did we not detect this before? Why did we not have this idea before? Do we not see relativity in our daily lives?
I think we do, but the fact is that we don't really experience it. It's not in front of our eyes. We can't see it, because as we're talking about objects that are going super fast, close to the speed of light, I mean, we'll never have the opportunity to get as fast as the speed of light, right?
Right, in our daily lives,
yes,
you mean,
it's
at
here,
least. Yeah.
But it's so little that we cannot observe it. It's almost non-existent.
So what you're saying is that basically the real world, as we see it in our human experience, is not a relativistic world.
I'm not saying that. I'm saying it is. It's just that we can't observe it because we're not going as fast as it should to be able to observe it.
So,
I think, yes.
so the theory of the Newtonian theory of mechanics, which is not relativistic, is close enough at low speeds for it to be good enough?
Well, yes, it's good enough because we can describe our world with the laws of Newton because we're not going fast, right?
Right.
But at the same time, yes, we can apply special relativity in our world. It would just be pointless because we don't need it.
Right. At least not in our going to work and coming back home and,
Exactly.
Okay. But if we're going into the world of science and research and observation and especially outer space, then we can't not take it into account.
Yes.
Okay. You mentioned some philosophical consequences and questions around this. Do you want to go into some of them maybe for us? Shall we talk about it?
I don't really have any example of how it revolutionized it. But we even studied time this year, and when the entire Earth thought that yes, it was obvious that a cause leads to an effect, or that there is a universal now, if we can say that. Obviously, when philosophers saw the theory of Einstein, they had to question everything that they had stated, because two events happening at the same time for one person could appear as occurring at a different one for someone else. And so I think it's still a topic today that philosophers that were writing before the Einstein theory, what they were writing was completely I don't really know how to say, but it
has to be reevaluated. It has to be rethought, right?
Because it has to be revalued by the philosophers that were born or wrote after Einstein.
Because, I mean, if we're putting into doubt the idea of causality, if we're putting into doubt the idea of some of the basic notions that we take for granted, then we have to reevaluate and sort of rebuild a lot of the ideas.
It's like restarting from zero, sort of.
Okay. But the actual special relativity side of things, you found it not that difficult in terms of the calculations, right?
It's not difficult, it's just that having the idea of it is difficult. I think what makes special relativity difficult for students like us is just the very concept of it that is kind of paradoxical for us.
Which is what is the best part of physics, because the idea is physics isn't just calculations, but it is understanding the physical meaning behind those calculations and that symbolism. And that's where special relativity becomes really special, I guess, in a way, is that to understand what you're calculating, what it means and what the consequences are, is quite hard to sort of accept in a way, right?
Yeah.
Okay. So did you guys did we go over most of the topic that you guys talked about, right? Is there anything that we forgot or do you want to bring up yourselves? Maybe just develop a bit more, or...
Well, I guess, as mentioned before, the special relativity apply when we're talking about particle physics. It's kind of hard, but like if you take example in particle accelerators,
yes,
where particles are sped up to near the light speed, their mass increase significantly and the time slow down for them. So when we are taking into account the relativity of Einstein, this allows for precise prediction of the energy and the momentum, because the theory can, so let's calculate the mass and how the time is going to happen during the collision of these two particles, so it can be very it will get very precise prediction, and so
right.
it will help for the study of particle.
So one of the things that's interesting, like you said, in particle accelerators, where we take particles like protons and accelerate them to like a thousandth or a hundredth of a thousandth of the speed of light, is that because of some of these consequences of SR, like the increase in mass, they become much more massive than we would feel. So you need a lot of force to be able to direct them around. For example, our circuit, which is circular, and you need a lot of energy, which is why you have these super powerful magnets that are very, very particular, that have to be employed to do this. Okay.
Yes.
Anything else, or have we kind of gone over most of the stuff for both of you?
No, I think it's mostly it.
Okay.
I think it was interesting when we had another presentation about cosmic rays, and I remember we brought up muons.
Yes.
And I think it sort of illustrates how special relativity is sort of everywhere.
Yes.
I didn't really expect it, actually, but so yeah, muons are a particle that are traveling at the speed of light.
Or very close to it, at least, yes.
Very close, yeah, at least. And so... yeah, no, it was interesting to see that.
So the idea being that cosmic rays, which is just very high energy rays from outer space, when they reach Earth's atmosphere, because of the collisions that could take place between them and some of the particles making up air, they produce very specific reactions, one of which produces a lot of muons. And these muons, which are very short-lived and travel at very high distances, we can detect them at the Earth's surface.
Yeah,
and that's only possible...
thanks to special relativity.
Right, because normally you'd say, okay, at that speed, with their lifespan, they shouldn't reach the bottom of the atmosphere, which is about 100 kilometers away, but they do. So we can explain that by saying, okay, because they're going that fast, in their time frame, time has slowed down, which gives it enough time for them to traverse the 100 kilometers. And on the other hand, because in their frame of reference, it's the Earth that's coming towards them at that high speed, the distance, which is 100 kilometers, gets shrunk so that in their short lifespan, they can traverse that distance. So it's a very, very sort of beautiful demonstration, illustration of the various consequences of special relativity.
Yeah.
Okay. So I'll ask you guys the same question I asked everybody else when we get to the end. What did you find particularly interesting in your topic, in the research that you did? What did you find particularly difficult or striking? Maybe Ryan, we can begin with you.
Yeah, so for me, the concept of simultaneity was really like mind-blowing, because it's, as I told you, it challenges everything. I was kind of surprised of how, as you said, we had to wait a lot of time before finding this theory, because thanks to Einstein. But so I really like the fact that it challenges everything, like the philosophy part, the science part. So I think that was the most surprising thing when I made my research.
Okay. And Rose, what about you?
I think the most difficult was the research, because we found just so much, and it was so beyond what we could understand, that it was a real work to, try to distinguish what was like possible for us to understand and explain, and keep the other informations for later, I would say. And we learned a lot. Obviously, we couldn't explain everything about special relativity because it's large. But no, it was particularly interesting to do this work of like selecting the right information and trying to explain it to people who have not dealt with math or physics for like 2 years.
Some of your classmates,
Yeah, and I was glad to see that some people did understand despite that. So it showed that we did
a good job.
Good job, yeah. No, but I like this. It was a sort of like challenge for us in terms of like research and stuff, but it was also a challenge for us to understand it and like be okay with it. Because as you were saying, it's complicated to take it for granted when we were not raised like that. This is not what we taught us about time whatsoever. And so we just had to like put everything away and just restart from zero, sort of.
And I think it's interesting because both of you guys doing math and physics at a high, rather advanced level, you were able to understand, at least go through some of the basic calculations yourselves. But then the question becomes, how do you go beyond just the calculations and talk about the physics to people who don't do that level, high level math and physics, right? Yeah,
because now it's not much about like the demonstration, because we did it, but it was not really about it. It was just a way to show that you can establish it even though you're not doing math or physics. Right?
The physics is not in the calculations, it's in the interpretation of those calculations.
And I think it's the interpretation that was a real challenge here.
Okay. Since both of you guys are going to be continuing to do sciences next year, is it at all any interest to maybe continue and try and get a better idea of what special relativity or even general relativity maybe in a few years talk about?
Definitely. I think all we know here is classical physics, right?
Yeah.
So I think it's complicated to like project ourselves because I believe it would be different, but it doesn't mean that it won't be interesting. And from what we've learned this year, I would love to learn more about it when we can. And I think it has a ton of applications and that each of them is super interesting, so definitely.
Yeah, I agree because of our level in physics, we couldn't really go further in these subjects. Also the fact that we couldn't work on general relativity, which is I think way more complicated, but I think
much more complicated.
Yeah, maybe in the future I would like to kind of research about it because I find it really interesting.
All right, well, maybe we'll come back to you guys in a few years once you've become experts in all forms of relativity, and then we'll see how things go. So thank you both of you for your presentation. It was really well done, and I hope you both enjoyed it as much as we did. Thank you very much.
Thank you so much.
Very much.
So that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.